In the last video, we have seen that searching in a binary tree is computationally not effective. A simple rule in arrangement of the nodes made all the difference, and we called that tree as binary search tree. Let me reiterate the rule of binary search tree. A binary search tree states that a parent as it's a binary tree, it can have only two children, a left child and a right child. So the rule says that a parent can have two children where left child is of lesser value and the right child is of greater value. So for example, if 5 is the parent, 3 can be on its left side and 7 can be on its right side. This arrangement makes a binary search tree. Let's see an example of a binary search tree. This is an example of a binary search. How can we say that? Here 5 is the root of the tree. So let's see its children. Its left child is 2 and its right child is 18. Yes, its left child is lesser than the value 5 and right child is greater than 5. So this portion of the tree is satisfying BST rule. Now let's see this subtree. So 2 is the root for this subtree and left child is lesser than 2, that is -4, and right child is greater than 2, that is 3. Therefore this is a binary search tree. Now let's see why searching in a binary search tree is easier than a binary tree. So let's take the same example here. Let's say that our search key is 2. To search for 2, we need to start from the root, that is 5. We have to compare the search key item with the root. Right now 5 and 2. So is 5 and 2. So 5 is greater than 2. That means an element which is lesser than 5 will stay only on its left side of this tree. So we have to move towards the left side. Then we compare the left side's root. Right now it is equal to 2. So 2 is equal to 2. Hence we have found the key. Now let's again try to search for the element 3 in the tree and see what's the pattern is. So first we need to start from the root, that is 5. Let's see, 5 is greater than 3, so it should be on the left portion of the subtree. So we move to the left subtree. Then 2, we compare it with 2. So is 2 is greater than 3? No. So that means the key will be present on the right child of this right subtree of this root. So we move towards the right. So and we compare with the current node. Current node is 3. So 3 is equal to 3. Hence we have found the element. The rule itself makes the search operation way easier than searching in a binary tree in recursive way or even in an iterative way. Now let's write down the pseudo algorithm for searching in a binary search tree. So here you can see the BST node which we have written in the previous video. So the search function will return boolean because search just tells us if the element is present in the tree or not. So the node value is integer. So we will be passing an integer value key. So how shall we do it? So as we have seen in the previous example, first the algorithm starts from the root of the tree. So we have to check from the root of the tree itself that if the key value is equal to root dot value, then we have to return true. This is the best case scenario where root itself is the value. But if not, we have to check the value if it is lesser or greater. So else if the key value is lesser than the root's value, if it is lesser than the root's value, we have to search on the left subtree. So before that, we need to check if it really has the left subtree or not. Sorry for the sudden screen change. There was a space insufficiency, but yeah. So continuing, if it is not equal to null, then we have to search on the left. So search on the left subtree and the value, and else if we have to check if the value is greater, if the value is greater. So if the key value is greater than the root's value, then we have to move on the right of the subtree. So we have to do the same check. If right subtree is there, then only then we have to search on the right side. So searching in a BST is comparatively very easy than any algorithm you might have seen. So, and also the search complexity is also very impressive. For an average case, the search is big of log n, whereas for a binary tree, for average case, it is itself big of n. In the graph, you can see the difference between number of operations performed when the complexity is big of n and big of log n. But there is a edge case to it. If the binary search tree is a skewed binary search tree, then it is the worst case scenario. For example, so this is an example of skewed binary search tree where 10 is the root and the elements are in such a way that it creates the node organization in this manner. So in this case, the search complexity will be big of n itself, and it is the worst case complexity of a binary search tree. So in this video, we have seen the search functionality and how computationally effective the binary search tree is. In the next upcoming videos, we will be looking at most common operations which can be performed on binary search tree, and I'll see you in the next one. Here we go!